Hello, I'm Mrs. Edwards, and today we're going to go over one more rule for differentiation, and that's going to be the product rule. But before we get to the product rule, I just want to quickly go over the rules that we have learned so far. Quick review here. Let's start with the power rule. You can use the power rule when you have something that looks like x to a power, and you just simply move the exponent to the front and subtract 1 off the exponent. So in this particular problem, f of x equals x cubed. 3 goes to the front, subtract 1 off the exponent, and the derivative of f would be 3x squared. Okay, the next rule, derivative of a constant, if you just have a number, 7, 12, square root of 2, 3/4, 0.7, 0, 9, any number off the number line, when you take a derivative, then you end up getting 0. So here we have f of x equals 7. So the derivative of 7 is 0. The reason it is 0 is because y equals a constant really just graphs a horizontal line. And the slope of the tangent at any point along that horizontal line is 0. Okay, the next one we have is the constant multiplier rule. And we use that first intuitively. When we saw 4x to the 5th, we were just thinking power rule. The 5 moved to the front and there was a 4 already sitting there. And so we just multiplied the 5 with the 4 and subtracted 1 off the exponent. So we use the constant multiplier rule. But a little more specifically, if you have any function and all of the terms are being multiplied by a constant, well then you can take that constant, set it off to the side, find the derivative, and then after you found the derivative, multiply that constant back through. This is actually a very similar rule to a rule we applied with limits. If you were finding the limit of something and what you were finding the limit of was being multiplied by a constant, you could set that number off to the side, find the limit, and after you found the limit, run that number that you set off to the side back through by multiplying it. So here's just a quick example. Here I have this function and all of that in black is being multiplied by 4. Okay, so what this rule is saying is that you could just find the derivative of everything inside and then afterwards multiply the answer by 4. Okay, so I found the derivative. Notice I had to use the power rule. X to the 5th is 5 to the front, x, subtract 1 off the exponent, 4. 6, x to the second, derivative of 3x is 3, derivative of a constant negative 5 is 0, and then run that 4 through because we set it off to the side. Okay, and we have our derivative. The sum difference rule, we've been also using all along. It's very intuitive. We actually used it right there. It's just saying that if you have a string of pieces that are being added or subtracted, that you can find the derivative of those pieces separately and then combine them at the end. Okay, all of these rules that we have learned so far, they are time savers. They allow us to not have to use the definition of a derivative in terms of a limit, which was a pretty time-consuming process. So what you're doing right now is you're building this bag of tricks. You've got these tools that you can pull out and use. But ultimately, you're going to have these problems in front of you that say, find the derivative. And eventually, it's not going to say using the product rule or using the constant multiplier. They will all be mixed together, and you have to know what rule applies. But often, more than one rule applies. So I don't want you to think when you check with the back of the book, when you check with Bob, and you see that it was worked out a certain way, and you didn't approach it that way, and you think, oh my gosh, I didn't even start it right. I don't know what I'm doing. There are multiple ways to do the same problem. And many of these rules can be applied to the same problem and you just go about it a little differently than somebody else, and that's okay. The only time that you have to use a specific technique is frankly when you first learn it, so that we make sure that you have that technique down. So if the directions specifically say, find the derivative using, and it lists a specific rule, then by all means use that rule. But keep in mind, lots of different rules can help you tackle a problem, and each rule kind of has its strengths and weaknesses, and you can't really get a handle fully on that until you've just done several problems. Here we have our new rule, the product rule. I wrote it out a little Dr. Seuss-like, I must say. We have here and there and everywhere. Ultimately, what this is saying is that we have two things multiplied together. This piece times this piece. I'm just saying here and there. To find the derivative, you're going to take here and multiply it by the derivative of there plus there times the derivative of here. The common mistake on this type of problem is to think that if you have two things multiplied together, that you can take the derivative of this one and the derivative of this one and then just multiply the answers together. You cannot do that. Danger. We could do that when it came to limits. Remember, if we were finding the limit of two things multiplied together, then we could find the limit of each of them separately and then multiply the answers together. So there is a reason why you might mix up these rules. But when you approach a problem and two things are being multiplied together, do not take the derivative of each one separately and then multiply them together. Use the product rule. So write this rule down and then move on. Here I have written the exact same problem 3 times. And we're going to use the power rule, constant multiplier rule, and then the product rule to find the answer, just so that you can see them side by side and realize it's okay if you take a different approach. All right, starting with the power rule. To use the power rule, you have to force the look of a number x to a power plus a number x to a power, that string of terms. So I'm going to distribute the 7. And then the 2 moves to the front, and I get 14x to the first power. Derivative of a constant 28 is 0. And then that is just 14x. Pretty darn fast, frankly. Okay, constant multiplier rule is just saying that we can set the 7 to the side. Just set it all the way over there. Don't care, not looking at it. Focus on the x squared plus 4. So the derivative of x squared plus 4 would be 2x to the first power, and then the derivative of 4 is 0. So we'd have 2x plus 0. And now that I've found the derivative of what's inside parentheses, I will multiply the 7 through. And we end up getting 14x. Okay, then our new rule, the product rule. I'm just rewriting it here to emphasize that the 7 is like the here, and the x squared plus 4 is like the there. So we're going to take the 7 times the derivative of x squared plus 4 plus x squared plus 4 times the derivative of 7. Okay, so when I do that, derivative of x squared is 2x, the derivative of 4 is 0, and then the derivative of 7 is 0. So one more time, since it's the first time you've seen the rule, we take the first piece times the derivative of the second one plus the second one times the derivative of the first one. Now we just need to simplify. 2x plus 0 is 2x. We have 2x times 7, and then all of that is times 0, so that's just 0. So we end up getting the same answer, 14x. One of the things that you might feel a little bit, frankly, frustrated with today is the product rule is a time saver, but you are going to often think today that it looks about the same. And sometimes the other rule might even look faster. But that's because we haven't taken derivatives of very many things yet. Like we haven't taken the derivative of exponential functions like 2 to the x, or we haven't taken the derivative of logarithms, or we haven't taken the derivative of trig functions. When we get to those derivatives, then the product rule will become something that you have to use rather than something that is another way of doing it. So you're going to be practicing the product rule today using easy basically easy problems. And that way, when we get to the harder ones, you'll have this basic idea down. The key in identifying when the product rule is especially powerful, I guess, or the faster way, one of the keys is just seeing that you have two things multiplied together, and both of those things that are being multiplied together have an x in them. Notice up here, yes, two things multiplied together. And hopefully, as time goes on here, you see two things multiplied together. Product rule, that's what I need to use. But the exception, always, if it's two things multiplied together and one of them doesn't have an x in it, you just want to use the constant multiplier rule. So here I have the same problem written twice. I really can't help myself because the product rule is, again, not going to be especially faster in the ones that you look at today. So it's good practice to make sure you can do it both ways. If I wanted to use the power rule, the first thing I would need to do is write those side by side and FOIL them. So first times outer times inner times last, and then combine those middle terms. And I have rewritten the function f of x in a different way, specifically in a way where we have a number x to a power plus a number x to a power. And then we can use the power rule, move the exponent to the front, subtract 1 off the exponent. Okay, so 4 went to the front, subtract 1, so 4x cubed. 2 went to the front, 16x to the first power. Derivative of a constant 16 is 0. Okay, another way with our new rule, the product rule, is we can take the red one times the derivative of the purple plus the purple times the derivative of the red. All right, so I'm just setting that up. Not actually taking the derivative yet. Okay, one more time, red times purple prime plus purple times red prime. Now I'm going to go ahead and find the derivative of what's here. So the derivative of x squared is 2x, and the derivative of 4 is 0. So all of this becomes just 2x. And same thing right there, the derivative of x squared plus 4 is going to be 2x plus 0. And then x squared plus 4 here and x squared plus 4 here. That doesn't change at all. Okay. And now we just want to simplify. So as I go to simplify, all I did was say plus 0 is nothing. Maybe a little overkill on the work here. All right, distribute the 2x through. Distribute this 2x here through, and then combine like terms, and we get the same answer. I think you would agree in this particular case, the power rule would have been a bit faster. Okay, but we're going to practice the product rule. Here's another one. We have two things multiplied together and they both have x's in them, so I'm going to use the product rule. You could multiply this all out by taking x cubed times each one of those, 2x squared times each one of those, negative 7 times each one of those to get the look of a number x to a power and use the power rule. But I'm going to go with the product rule. Just setting that up here, we're going to have this first one multiplied by the derivative of the second one plus the second one times the derivative of the first one. All right, so there's my first one just brought down. Now let's find the derivative of what's inside here. The 6 moves to the front, 2/3 times 6. The 6 and 3 cancel, giving us 2 times that 2. So we have 4x to the 5th. The derivative of negative 4x is just minus 4, and the derivative of 1 is 0. So we've written down the first one times the derivative of that second one, plus, and then we have the second one times the derivative of the first one. So the derivative of x cubed is 3x squared, the derivative of 2x squared is 4x, and the derivative of minus 7 is 0. We have done the calculus. The calculus is done. Now, simplifying is a lot of algebra, and I would need to take 4x to the 5th times each one of those, negative 4 times each one of those, 3x squared times each one of those, and 4x times each one of those, combine, and voila! That would be our final answer. Kind of just a side note to plant, in the back of your mind is there are times where you don't have to simplify, because what if I wanted the derivative evaluated at 3? Well, I wouldn't need to simplify. I could just go into this one and replace all of the x's with 3, get my final answer, and I would never worry about what is the simplified version of y prime. Woohoo! Our last example. Okay, so we've got this function, and we have all that ugly stuff multiplied by all that ugly stuff. But main thing we see is two things multiplied together, and they both have an x in it. So we're going to go with the product rule. You could, of course, multiply these two together by taking 3x to the 5th times each one of those, 2x to the 4th times each one of those, negative 6x to the 1/2 times each one of those, and negative 1 times each one of those, combine like terms, and then you'd have that look of a number x to a power plus a number x to a power, and then you could use the power rule. But I say, for this power rule, no thank you. Oh, that looks hideous. All right, so let's just stick with our new rule, the product rule. And so we have that right there. And then ultimately what we're going to do is we're going to take the red times the derivative of the purple plus the purple times the derivative of the red. Okay, so starting that off there, I have the red times the derivative of the purple. Now I actually stopped a moment ago and I was going to fix this slide, but I decided, it's kind of a teachable moment. Notice here I went red times the derivative of the purple, derivative of red times the purple. Okay, it doesn't matter. This right here is commutative. There times here prime, right? You just grab one, multiply it by the derivative of the other one, plus grab the other one and times the derivative. So it doesn't matter that these two are out of order. It just matters that we have these two multiplied where the purple one had a derivative, these two multiplied where we had the red one's derivative. Okay, so enough said with that. Let's go ahead and find the derivatives. We'll ultimately just drop this red part down to the next line and this purple part down to the next line because we don't need to do anything with it, but we do need to take the derivative of this purple piece and this red piece there. Before you can take the derivative, we need to make it look like a number x to a power so we can use the power rule. That's just emphasizing that we have some derivatives there. Okay, so that one right there, how can I rewrite that? It's going to be inside out, x to the 2 over 3. So that's going to be 12x to the 2/3. Okay, and then dividing by 2. Dividing by 2 is the same as multiplying by the reciprocal, so multiplying by 1/2. So I'm going to rewrite this one as minus 1/2 x squared. Okay, then over here, I'm going to ultimately, again, just drop that purple part down. I don't need to do anything, but the derivative, I do need to rewrite this one so I can use the power rule. So x, the exponent on x is 1, and this is the square root. So inside out, inside exponent is 1, outside there is 2. So this is x to the 1/2. So we're going to rewrite that as negative 6x to the 1/2. Okay, otherwise, everything else stayed the same. And now I can actually take the derivative of these two since the terms are written as a number x to a power. Okay, starting with that one, the 4 comes to the front. 1/2 times 4 is 2, x to the 3rd. The 2/3 comes to the front. When you multiply 2/3 times 12, that's 24 over 3, which is 8. Okay, and if you subtract 1 from the 2/3, 2/3 minus 1 is 2/3 minus 3 over 3, so we have negative 1/3. Okay, then this one, the 2 comes to the front, negative 1/2 times 2 is minus 1, subtract 1 from the exponent, so just x. I know pi looks so crazy, okay, but pi is just the number 3.14, etc., etc. It's just a number, it's a constant. I know it looks like a variable, but it just represents an unchanging number pi. So the derivative of pi is 0. Okay, so we've got our derivative. We also need to take the derivative of this part here. So 5 comes to the front, and we're going to have 15x to the fourth. The 4 comes to the front, 8x to the third. 1/2 comes to the front, -6 multiplied by 1/2 is -3. 1/2 minus 1, subtracting 1 from the exponent. 1/2 minus 1 is like 1/2 minus 2 over 2. Okay, so we have -1/2, and then the derivative of the constant -1 is 0. Okay, so we found the derivative, and then that one is just going to come down, and that one is just going to come down. Okay, we have done the calculus, right? We have found the derivative. All of this, yada, 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 is the derivative of f of x. So f prime of x equals all of that. Now, ultimately, we could simplify by, and we're just like, no, tell me I won't have to. No, you won't have to do any this hard in your homework. And I say the same thing. No, thank you. Okay, so we're not going to simplify that one together, but hopefully you have the power rule down now. When you see two things multiplied together, do not make the common mistake of taking the derivative of this one, the derivative of this one, and then just multiplying. You cannot do that. You're going to take the first one times the derivative of the second one, plus the second one times the derivative of the first one, and then you have taken the derivative. The exception, especially, of when you want to skip the product rule is if the two things multiplied together, one of them doesn't have an x in it, it's just a constant. Set the constant out to the side and only take the derivative of the one piece and then multiply that constant back through. Okay, I think that your tool belt is getting full. Get to work.